Hello, it's Greg Taylor, and welcome to Demo Lessons. So today, what I'd like to talk about is multiplication. Multiplication in general, from regular numbers through integers, through rational numbers, or the basics of multiplying fractions. Okay? And what I want to do is I want to build the capacity for learning. All right, so I'm not going to do like a lot of mock lessoning and signaling and what have you now for the discourse method, because I want to focus on the building capacity piece. All right, now I might break into it now and then, but mostly I want to talk to you, the teacher, about why it's so important to do this. All right, so if we're assuming knowledge, right, then we're going to end up disappointed. That's just in general the way it is. If we're assuming knowledge, we're going to end up disappointed. So what we're going to do is we're going to assume no knowledge, and we're going to run with this lesson. It's going to seem rather rudimentary, but believe me, if you take the calculators away from them and they begin to have to do this in their head, some students will really flounder because they don't have their multiplication tables memorized. And they struggle with what multiplication truly is fundamentally. So this is going to build up all those concepts. Okay? So let's go ahead and begin. All right, we're going to start with something simple like 6 times 3. 6 times 3, we can think of that a lot of times. A lot of different ways, I should say. But one of the ways we can think about this is to consider what times means. What it means is either 6 will appear 3 times or 3 will appear 6 times. So it doesn't really matter how you do it. For instance, let's ask the students to go ahead and create a symbol that helps them to decide what this is. So now they're not just doing an algorithm or a memorized thing. They're doing some kind of graphic. And what I would suggest is a strip diagram. Now my strip diagram, I can say, okay, here's my strip. My tape diagram, sometimes it's called. It's a piece of paper or tape that I could cut and draw onto. All right, what I'm going to do is I'm going to draw onto it 3 squares or 3 sections that are roughly equal in area. The notion is they should be equal. And if I'm working with manipulatives, at this point I would take 3 colored squares and put them together. And that would represent what? So it was a 1 before I divided it up, but now it's a 1 and a 1 and a 1, right? So I'm going to go ahead and just, in this diagram, I'm going to go ahead and just, my phone's going crazy, I'm going to go ahead and just put 1. So clearly that's a 3. Yes? So far so good, no one's going to struggle with that. Now the next thing is, okay, so now if that's 3, and this says 6 times 3, how many times would 3 appear? I'm trying to drive in that notion when I'm asking students questions like that of times, right? Times. Times means multiplicity, right? Therefore multiplication. So this is going to appear, if I've drawn a 3, it's going to have to appear 6 times, right? If I had drawn a 6, it would have to appear how many times? 3 times. All right, so this seems silly and rudimentary to middle school and high school teachers, but it isn't necessarily silly and rudimentary if you're struggling, okay? It's necessary, and it might need to be shown in a few different ways. I would have those manipulatives on the table, have them make a group of 3, then make separate another group of 3, and another group of 3, and another group of 3, and another group of 3. 1, 2, 3, 4, 5. How many times should it appear? That's right, 6 times. Okay? So what do we do now? Well, now what we do is what's called repeated addition. We do 3 and 3 and 3 and 3 and 3 and 3, right? That's what we do. And how many times did that 3 appear? Well, it appears 6 times, doesn't it? So here's the deal. We catch kids counting on their fingers and no, you need to memorize. You need to, hey, whatever. Yes, it's very beneficial to know some multiplication tables in the 12 by 12 or the 13 by 13 table is a nice one to know. At least 10 by 10, right? So all those things, those strategies for memorization, those are a separate issue from this. This is building capacity. I want them to understand what multiplication fundamentally is. So look, if I have 1, 2, 3, 4, 5, 6 threes, 1, 2, 3, 4, 5, 6 threes added together, what am I going to get? When I count them up, I get 3, 6, 9. Now counting by threes, that's called skip counting. And that's a skill they should have. They should be able to count by 2s, by 3s, by 5s, by 10s, right? Skip counting. Skip counting begins to build the table, right? If I say 3, 6, 9, 12, 15, 18, I'm saying 3 times 1, 3 times 2, 3 times 3. You see, I'm beginning to remember through the process of skip counting what 3 times 2 and what 3 times 3 and what 3 times 4 is, because I'm using a strategy that makes it meaningful. Oh, it appears 6 times, and I skip counted 3, 6, 9, 12, 15, 18. So 18 it is. All right? 18 it is. Did that work here? 3, 6, 9, 12, 15, 18. Absolutely. 18 it is. Right? So 18 it is. So that's 2 ways. This is with your manipulatives and the drawing your strip diagram on the board, going from concrete, the manipulative, to symbolic, the strip diagram. Okay? But notice we said that we could also do 6. How many times? Exactly, 3 times. So let's do that and let's check ourselves. Now, when I'm doing this, this isn't for you, the teacher. This isn't for you, the teacher. This is for the student. I'm showing you what I would do with the student. And I would ask more questions, and I would get more responses, and I would ask for multiplicity. I would let them tell me I could do this or that. I would let them tell me that's the same thing as that. I would let them tell me, yeah, I can add them all together. If I don't know how to multiply, it's okay. And I'd ask questions, and I would have them talk to one another, and that would build up that capacity. I'm just skipping that part now because I don't have a class. And I did a couple of them, but it's a little bit contrived. In the first 2, I had to say, yes, that's right, too many times because there was no one giving me feedback. I would never really say, yes, very good, that's right. I would say, does that sound right? And I would get consensus from the group. So on those first 2 videos, every time you saw me say yes, I would have been asking for consensus from the group in the discourse method. Okay? So let's take a look at it. That's 1 strip, 2 strips, but I need to have strip how many times? I need to have it 3 times, right? So let's do one more. Okay? And again, that would be 6 and 6 and 6, right? That's what that would be. Which means I could write that as 6 plus 6 plus 6. Again, can I do repeated addition? I absolutely can. Can I skip count? I absolutely can. If you can skip count by 6s, you can skip count by 5s. How about this? 5, 10, 15. I did 3 times, right? So how much less than 5 is 6? It's 1 less, right? So if I skip count by 5s, because I'm good at that, 5, 10, 15, I know that I've got to add 1, 2, 3 at the end because I only skip counted 5s. This is called making numbers more friendly. All right? And I'm pulling my ones out of it to make it a 5. And then I'll put my ones back in at the end, and that's totally fine. In fact, that's very algebraic. The notion of decomposing and recomposing numbers is essential to algebra skills. These algebra mindsets, these algebraic thinking skills are built in the arithmetic that they learn, except they learn them algorithmically. So those algebraic understandings are gone, and that's why so many of us, of our students come up and they are fundamentally unable to do algebra. They can't think through the logic of it. And when we show them, try to put it into their brains, it doesn't work, and we wonder why. And we do it more and louder and faster, or slower and louder. None of that's going to make a difference for most of the kids. For some, for a few, it will. But if I start out building this fundamental understanding, and I do it a few times, I do it with do nows, even for the kids who are advanced, are kind of bumming out, 1 or 2 times, that ain't going to kill them 1 or 2 classes. They're going to be much more frustrated sitting through memorization facts and algorithmic facts that we want kids to know, trying to catch them up. Let this happen a couple of times, and then when you station off, people are still struggling, you can have manipulators and have them working and writing and drawing and build that capacity. Okay? So this is 5, 10, 15 plus 16, 17, 18. Those 3's make 18 again, don't they? So what have we shown here? Just fundamentally, if you look at this, what we've shown is a number of things. We've shown that I can skip count and do a multiplicity of additions, and that it will equate to multiplication. It begins to make that concept solid for me. But also, I've shown that 3 times 6 is the same thing, or is equivalent to 6 times 3. Algebraic principles, right? Associative and commutative properties, how I group things, or if I can do them in opposite orders. These skills and these understandings, even if they aren't named, are being ingrained here. And I can name them. I can name them, right? I can say, hey, this is that property. Look at that. And let them discover it. Start having them use vocabulary when they speak about them with their groups and out into the class. Not just to me. In fact, I want questions to be directed at each other and answered by each other and not at me, because if they're always answering me, I'm the center. I'm trying to get myself out of the center, step aside, and let them do the math. Okay, it's very, very important. And this is going to be built through the discourse model. So when we look at this, we see that this kid easily could now, this is the beauty of the manipulators. I could say, okay, take a pencil or a stick or the edge of your book and just push these together and push these together. And what happens? And what happens is very, very important. Obviously, we see what happens, right, as teachers, but it's not always so obvious for the students. What we think is obvious, it's not always obvious. So what happened? Well, what happened was this. I basically had a big group now, all pushed together. 1, 2, 3, 4, 5, 6. All right? And, all right? Same thing here. I'd have this group all pushed together, right? Imagine I'm a better artist than I am right now. Imagine those are all the same size. Here, let's make it a little easier to imagine. Okay. So now, for now, I'm going to ignore that one, and we're going to focus on this one. So this is 3, what would we call those now? And then I would begin to talk. I would ask them questions. What might we call them? Does anybody think? I would tie it to the world. Think about architecture. Maybe like see the Capitol building, or you see it fancy, and it's got this big beam and then these things holding it up. You know what they call those pillars, right? There's another word for them. It starts with C, and it's columns. Remind them about columns are vertical because columns are vertical out in the world that they deal with. They're named columns because That's what we called those things, columns. Before we made a matrix, we were making posts and beams, okay? So now I asked them, well, okay, it's 3 columns. Well, what would I call these parts then? These parts that don't go up and down. And of course, those parts would be uncovered through discourse as rows. And how many rows are there, right? And then we would see it. We say, oh, there's 1, 2, 3, 4, 5, 6 rows. And why is there 6 rows? Because we wrote 3 6 times, right? Now, if I look over here, I have 6 columns, all right? 6 vertical pieces of that when I pushed those manipulatives all together. However, when I look at the rows, I see there's only what? 1, 2, because 6 appeared 3 times. That's what we're saying here, right? So now, if I ask them what's 6 times 3, they could draw a box. They could cut one dimension of it, length or height, whatever, into 3, the other dimension into 6s. And now what I have is a box. How would I describe that shape, the shape of that box? Now I would start talking again about, descriptions and verbalization. How could I talk about this box? It's something, something and something. How can I talk about its shape? Sooner or later, someone's going to say it's 6 by 3. By. 6 by 3. Okay. So then I asked him, well, 6 by 3. That doesn't look very mathematical. I wonder if there's a way to make it look more mathematical. What can I put in place of the word by? That still means the same thing, and someone's going to give you that X. This means 6 by 3. But that doesn't just mean 6 by 3. What does that X also mean? Right. It means 6 times. Right? So it means both things. But what's the one we care about the most? Well, the one we care about the most is the one that they understand the best. So don't get caught up in that. Because they get 6 by 3, and they start thinking about it that way, and they count the squares, and they realize that a 6 by 3 has 18 squares. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18. Did I say 17? I meant to say 18 if I did. 18 squares. And also I could say, well, what if it was 5 by 3? 5, 10, 15, 16, 17, 18. All those strategies that we do with the manipulative separated can still be done with them grouped together, or with the symbolic representation that we have right here. So this is 18. So if 6 times 3 is 18, and 6 by 3 is also 18, what does the 18 mean then? 18 what? Here we said there was 18 squares, right? Because that's what I counted. So let's check this one. Is 3 by 6 going to be the same thing as 6 by 3? And some kid might say, I might just tell the kid, hey, if I have them do their manipulatives, sometimes what I like the best is I give paper plates, and they put their manipulatives on it, because then I can have them twist them sideways or turn them upside down. So if I'm using fractions or ratios, this is a convenient time when I say, spin your plate sideways. Does it look like that now? Can I just spin this way or that way? Are they not really the same thing turned 90 degrees? We can talk about rotations now, begin to get some geometric knowledge. Also, what is 6 by 3? If this was a room, and I counted these squares, if that was the squares that were going to be like tiles, what did I find out about that room? And we can begin to get that discussion going, and sooner or later someone's going to come up with the word area. So what have we done here? By going into the rudimentary math that no secondary teacher wants to contend with, we've exposed all kinds of relationships, as well as area. Okay, as well as area. So what we're doing is we're getting more and more understanding about how math comes together, and that's the whole thing with the integrated math standards and Common Course standards. We can do them separate, but if we quit trying to separate the math and we just start to kind of let it come together as it naturally does, we'll find that the integrated methodology is far better. I can tell you this for practical speaking, because I've done it with private students and tutors, and I've done it as a martial artist for a long, long time, integrating a huge amount of martial arts skills into one system and letting them unfold as they do. I organize them for testing in blocks that made sense, but when we train it, we explored all of those things, and then we come back and explored them again and explored them again. That's called spiraling, and that's what you're doing now. You're exploring this again, and for some students, this might be the first time they've ever explored it this way. And so guess what? You might need to revisit it, and don't be afraid to revisit, because you can revisit it more quickly. Okay? So now, look at this. I want to ask you this. Now, we can do all the math we want. We can make this 10 by 15 or whatever. It gets to be cumbersome, right? But we can do that, and we can break a 10 by 15 up into, 2 pieces, multiply them both together, and then recombine them. That's distribution, right? That strategy is there. So if these get bigger, we can separate them, multiply, and then recombine the products and to get the overall product. Okay, that's just algebraic thinking again. So important, and we wonder so often why they can't understand it. This is why. We need to do more of this, and don't be afraid to spend the time on it. It will reap great rewards throughout the year if you take care of this right up front. All right, well, let's look at one more aspect of this before we go on to fractional pieces, and let's look at integers. What if I said how does that change things? Well, if you watched the video before, you saw me do a sort of mock demo of a discussion with no students, obviously, to unfold what negative meant. And in a nutshell, to unfold it here, when I'm on the number line, I'm going positive to the left and negative to the right. Left is the opposite of right. So when I put a negative sign in front of a number, I'm basically saying the opposite of that number. Not 5 to the left, but 5 to the right instead of 0, of course, thinking of 0 as our starting point. So when it's certainly what splits negativity. And let's just say this right now. 0 is neither negative nor positive. You should know that, but make sure you talk to your kids about that. It's what's called non-negative. It's not positive because I can't say, oh, there's the 1 0 of, I have that nothing. Yeah, I have a positive no money in my hands. But I also don't have a negative no money in my hands, right? I just have no money. It doesn't have a positive or a negative sign. It's in the center, and that's what 0 is. It's a non-negative number. It's neither positive nor is it negative. So, but if I say these words, 6 times 3. So if I say 6 times 3 is that, I ask myself, well, what kind of 6 is this? Here it was positive, but what did I change it to? Negative. And what kind of 3 is that? Well, did I put a negative in front of it? If there's no negative in front of it, guess what that 3 stays? It stays positive. So let me just put it in here for now. All right? This is why. Because when I'm multiplying signed numbers, I want to speak the sign as the phrase the opposite of. Now, I don't want to say it more than once in any sentence. So if there's more than one negative, I say it with whatever one last one, first one, I don't care, but only one. So what's the opposite of positive? That's an easy question to answer, isn't it? Not what's positive times negative. That may or may not come out that quickly. What's the opposite of negative? Positive. What's the opposite of positive? Negative. They're going to spit that out at you like they were on fire, okay? Because it's easy. It's logical. It makes sense. It's tied to knowledge they feel confident about, and they're going to put it out there. They know the opposite of right is left, the opposite of on is off, the opposite of positive is negative. They know those opposite relationships, the fully contrasted relationship. They understand many of those. Use that understanding. Don't be afraid to do it differently, because they need different strategies than we did. We came with a different set of bases that we built upon. They're not coming with it. And we're now having to reinstitute that. We got off on a tangent of just teach them this, just teach this quick way, teach this algorithm. All they got to do is this so they can problem solve. They can't problem solve because all of those things the algorithms represented, that was what built up problem solving skills in the brain. That's what built up the perseverance for the student. That's gone. So we got to bring it back. Okay? Now, what if I said this? Ooh, wait a second. What if I said this? Can you see that my model doesn't change a bit? Right? My model doesn't change a bit. And I can do it right here. What's the opposite of negative? What's the opposite of negative? What's the opposite of negative? Well, the opposite of negative is what? It's positive. They're not going to forget that. Okay? So, real quickly, that was just to sidetrack you into seeing how sign numbers are going to be just as easy as regular numbers if you teach them the simple phrase, the opposite of. And instead of talking about how of means multiply, because it does sometimes and it doesn't others. Like and means add sometimes and not others, right? So they've got to have that nuance, but right now the opposite of has the of built in, right? And when the of is built in, we can later talk about how that of oftentimes means to multiply. Because what did I do with these? The opposite of. I did the opposite of negative, and the of kind of implied multiplication, but it doesn't always. Because if I was combining those integers, I would still ask about a double sign in the same way. Okay? All right. Let's close by looking at how you can use the same model to multiply fractions. Okay? So what if I didn't have 6 times 3 up there? I didn't have that at all. What if I had 1/6 times 2/3? Okay? Now we know that when I'm multiplying fractions, I don't need a common denominator, but the students might not know that. And they always, when they learn common denominators, they struggle with it, and then they want to misapply it. When they learn to multiply, they want to just add bases of or denominators just like we multiply them. So let's show them why this works. And we can tie it back to the multiplication. Say, remember when we multiplied, we had, what's 6 times 3? We had them draw a box, right? And cut it up. And then what would that be? How many squares are there? 18. So now they've got all that knowledge we just talked about. I said, what if I, just like I did, what if I did this? Ooh, how would that be different? Well, which side of that box do you think would represent thirds? Which side of that box would represent the thirds part? And of course, they're going to come pretty quickly to the realization that the side of the box that measures 3 units, right? 3 squares long, or 3 squares tall, right? So they're going to say, oh, well, here is the 3 part, okay? This is the thirds, okay? So if you think about this square, if I cut it like that, I'd really cut it into 1/3, 2/3, 3/3, right? If I just cut that out, each one of those would be equal. There would be 3 of them. The 3 of them would make a whole. Do you see it? So this is, instead of putting 3, let's put thirds. Okay? Just to not confuse them. But I think many of them will understand it. Well, and obviously, if this side represents the thirds, which side is going to represent the sixths? Is the side that's cut into 6. And again, if I just cut this into 6 pieces, and I stack them up, each of those strips would be the same. All 6 of them together would make the whole. So this is cutting that rectangle into 6. Right? Now, what am I going to do to figure out how to know what that final fraction is? And we can we can estimate or predict, and we know the algorithm, but we're not gonna tell the algorithm. You see, you don't tell the algorithm. Same thing with the multiplication, but it really comes through in the fractions. You let them do 2 or 3 or 4 of them, asking them questions, having them talk to each other, asking them if they can find any patterns, write about their patterns. Someone's going to come up with, hey, look, they did it this way, they did it this way. They write it symbolically. They do it graphically, they do it graphically, they write it symbolically. Then the abstract will kick in. Look at the pattern. I'm seeing beyond what's symbolically written, a pattern that's in my brain. Now abstraction's taken place, and you've risen them through the Piaget levels. That abstraction is supported with symbology and graphic understanding, which they can articulate with words. So here's how we would handle that. We would say, okay, let's do what's called hatching. Hatching is an old draftsman tool. When they used to cut something in half, they would hatch the drawing to show where it actually was cut and which parts were voids, didn't have hatches. So what I'm going to do is I'm going to say, okay, well, let's hatch how many thirds? 2, right? Which part is the thirds? The columns are the thirds, right? So I'm going to hatch 2 of the 3 columns because that's how much I have. I have 2 of the 3 possible pieces of that whole, right? Voila. Okay? On the other side, where will I hatch? And it doesn't matter how I hatch. I tend to hatch in groups, but could I say, well, there's a piece, there's 1/3, and there's another third, and that makes 2/3? Could I do that? I absolutely can. There's no benefit to doing it this way over that way. Simplicity, maybe, of it when you look, but honestly, it doesn't matter. So let's move on. Let's let them hatch it however they want. Let them group it however they want to group it. They're going to group it into thirds and get 2 of those thirds hatched off. Then they're good. So now I'm going to look at the 6. And how many 6 do I have? Just one of them. I'm going to hatch one of them. Okay? Doesn't matter which one. I can hatch any one. I'm just going to hatch this way. That's one of the 6 possible pieces. Here, again, any one of them. Here's one of the 6 possible pieces, right? Is that not 1 out of 6 and 2 out of 3? The same way this is 1 out of 6 and 2 out of 3? Absolutely. Okay? And we could even talk about this being a, 1. Well, let's not talk about that. Thinking about tying it to area, but let's not confuse it. Let's keep it simple. Now, how do I know what the answer is? I count what's cross-hatched. That's where hatches cross. Hatches cross. Okay? So where did hatches cross? Well, hatches crossed right here, didn't they? Let's look over here. Hatches crossed here, but not in the middle, and here, because I colored it slightly different. You see, so this gives you a simplicity of viewing, but this still gives you the same logic, and don't steer a kid's logic to make more sense to you. Help them use their logic to find the way that makes sense to them. They can translate it into your way later when they have a more full understanding. Okay? So, let's see what we've got. We've got how many crosshatched? We've got 2 crosshatched, right? So let me go ahead and do this. 1/6 times 2/3 equals. So how many were crosshatched? Crosshatched, 2. Okay, that's the number of crosshatched squares. So I've got 2. 2 out of how many? Well, this is where it's easy. How many squares is in a 3 by 6? It goes back to, can I do 6 3 times? Can I skip count by 5s and add 3? Can I do 3, 6? Can I skip count by 3s? But what I'm going to still come to is 3 by 6 is 18 squares. So this is the number of total squares, right? Now, is that answer correct? It absolutely is. And if they could get only that far and get it correct every time, you could be proud and happy because the rest will be easy. But what I want to say to them is that, oh, look at that. Like, each of these are even. Huh. Now, if I ask myself about even numbers, I might ask myself, what are these even numbers built of? Halves and doubles. And that's when that halving numbers and doubling numbers from elementary school becomes quintessential, right? When I'm talking about even number reduction, I like to call it simplification, because the value of the fraction doesn't reduce. It's the same value. It just, the numbers get smaller when I simplify it. So what I'm going to say is, well, what's half of 2? And what's half of 18? Right? So, well, why am I picking half? Because they're even, and every even number divides by 2. So if you're going to tell them something, tell them that. So how many times does 2 go into itself? Let's take two squares in your plate, right? 2, and let's cut that pile in half. How many is in each pile? It's 1. Then I can take my 18, right? And look, I could cut that in half pretty easily, right? This right here is half of 18, isn't it? Right? It's a little bit hard to think about cutting 3 in half because it's an odd number. When I cut an even number, so half of 18 is 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's my reduced answer. Again, I could expand it to count it as signs numbers as well, right? I could say, ooh, well, what if it was negative 1/6? Well, then my negative would be here, right, or here. And what's the opposite of positive? All right. Straightforward. What if it was negative 1/6 and multiplied by, I should say, negative 2/3? Well, then the thirds part is negative as well, right? And what's the opposite of negative? It's positive. Right? Okay? So this is how you take colored square manipulatives, build it up from concrete to symbolic through strip diagrams, and collecting them together to create solid objects which we can draw and divide, begin to get our mental math. Talk about that as a product and as an area of squares if I wanted to tile that room. Bring it into reality, okay? Carpet squares for the basement, right? In the old days we had blue chip stamps and green stamps, and you'd have to fill up the page with stamps, and so you could talk about stamps on the blue chip page, but I don't think that really applies anymore. I'm old. But what I'm trying to say is this. I build up from concrete to symbolic. I refine the symbology. I have them manipulate the symbology. They look for the patterns in the numerical analysis and the symbolic analysis until they discover, look, what did I really do? I really multiplied the top times the top and the bottom times the bottom, and boom, out pops from them the algorithm. How do I multiply fractions? Oh, I multiply the tops and I multiply the bottoms. And now they know why. If they forget, they can draw a picture, cut it up, count the squares, reduce it, or simplify it, I should say, and there remind themselves of the answer. And then the algorithm would probably pop, oh yeah, I remember it now, I just multiplied these. But you teach them to unpack their knowledge through discourse in the lesson, and then they can unpack their knowledge when they're struggling on a problem alone or in a small group, giving them perseverance and multiple strategies to solve open-ended problems. So I want to rest this class with this. This is the strategy to build capacity all the way up through the multiplication of fractions. And I want to thank you for your time.